Okay, we can start talk about our soil liquefaction's evaluation. So we can talk about the evaluation part now. And that's three steps, or that's like a three main part when we come to evaluations. First is the soil liquefactions susceptibility. So we first we check whether the soil is susceptible to be liquefied or not, because liquefactions is for sand, right? And if it's a clay, then we don't worry about soil liquefactions. And it comes to tricky when you have silt, because silt is between sand and clay. So that would be like, the bottom line case that you need to spend extra effort to investigate whether it is susceptible to soil liquefactions. So we talk about the susceptibility maybe 2 slides later. So the soil type, so when we talk about the susceptibility, is about the soil type and also the groundwater, whether like your soils will be saturated or not. So that's our first step. So this become very important when we talk about the evaluations of soil liquefactions. So if the soil is susceptible to soil liquefactions, then we will look at the triggering. What it takes, how much loading it takes for the soil to liquefy. So you can think of this part. This is comparing the resistance, so soil resistant to liquefactions, and the loading. So the loading is from the earthquakes. You try to compare the loading versus the soil resistance. And third is the consequence, and that's two parts we talk about later: settlement and lateral spreading. So each steps, there's like a sequence there. So if the soil is not susceptible to soil liquefactions, then you're pretty much done. You don't need to, move on to step 2 and step 3. But in the case that yes, the soil is susceptible to soil liquefactions, then you ask these questions whether the loading is enough to trigger soil liquefactions. Then we do the second steps. And if the answer is yes, the loading is large, will be like enough for triggering, then you also need to estimate the consequence when liquefactions happen for a project site. So the remaining for this lecture, we will focus on these three items: susceptibility, triggering, and also the consequence. So first, before we get to the susceptibility, let's talk about some terminology. First, if we talk about the CSR, which is the cyclic stress ratios, and CRR stands for cyclic resistance ratios, and the R sub U is the excess pore pressure ratio. We talk about this in the cyclic simple shear test. So cyclic pore pressure ratio, and the N is the number of loading cycles to trigger soil liquefactions or to liquefactions initiations. Or in other words, it's the number of loading cycles to which RU equal 1. Right? Because we talk about this when the excess pore pressure ratios is equals to 1, then that is the point that the soil has lost all the soil strength. We also talk about this too. The gamma is the shear strength, and the tau is the shear stress. And the graph here on the left shows you the cyclic stress ratios, the CSR versus the N. So here the this graph or this curve here, so you get like a different soil type or different like a relative density. What we call this is the soil liquefactions resistant curve. So this is soil liquefactions resistance curve. So this is like established from experimental data. So you know each data points here represent one cyclic simple shear or cyclic triaxial test. So they investigate how many number of cycles to reach the liquefaction's initiations. So for examples, here is one data point. So it takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about 10 cycles to reach like or actually like about 8 cycles to reach R equal 1. So here like it takes like 8 cycles for us to reach R equal 1. So n equal 8, and the CSR cyclic stress ratio is equals to the input shear stress divided by the vertical effective stress. And we know that the vertical effective stress for this case is 100 kilopascal. And the shear stress here is like 15. So it's 15 kilopascal divided by 100 kilopascal. So we got 0.15. So for this cyclic simple shear test, we know the CSR equals 0.15 and number of cycles reaching failure is 8. So if we go back to here, so if we try to establish like a data point for the particular sand that we work on, so we know the CSR is like a 0.15 here, and this is 8 right there. So we got one data point there. So the soil liquefaction resistance curve depends on the soil type. So if you work on like California soil versus Japanese soils, you know the sites that you work on, you know the sand, you try to model, and also with the particular density, you know, you will change too. So the same soils, different density, you will have different like liquefaction resistant curve here. But anyways, like you try to do a couple tests with different loading amplitude, then you will be corresponding to a different number of cycles to failure. Then you will have a couple of tests, then you can like draw the line and then establish the soil liquefaction resistant curve. And this curve is in a semi-log scale. Again, like the x-axis is in a log scale, but the y-axis is not. So the equations for this capacity curve is CRR. So or like this case, is the the cyclic stress ratios will be corresponding to the soil liquefaction's resistance to resist like liquefactions to be happens. So you can call it CRR or CSR, but like in practice, people usually call it CRR. Because in that case, we equals the CSR equals to CRR for the effective safety equal 1 scenario. This equals to A times N, so the x-axis N, and then negative B. And A and B are soil dependence, like a shape factor. So if you have different type of soils, then you change the A and B. And some advanced modeling in FLAG or like other finite elements models, they take the parameters A and B to to customize the model to accommodate the different type of soils and also different type of density. So again, we talk about the cyclic stress ratios, which is equals to the loading amplitudes, the loading shear stress divided by the vertical initial effective stress. And the CRR, like this case, we can establish like in laboratory data, or we can establish in field data. We will talk about later. And at the end of the day, like at the end of the day is this soil liquefaction's resistance curve is the one that we try to establish to describe the resistance of the soils to liquefactions in a laboratory setup. So this one you will think about the soil liquefactions, and for the excess pore pressure, with RU equal 1 is failure. But if it is less than 0.3, we consider this is low. So this is still in the cycle mobility range. When you get to 0.4 and 0.5, you still consider like, maybe okay. But when you get to 0.6 to 0.9, it starts to be dangerous. So how much excess pore pressure that being generated would cause you concern? I would say about 0.6. That to be quite dangerous. So here you start to worry about getting to the full liquefactions type of failures. Here is more like you're still in the cyclic mobility. Again, the cyclic mobility and the full liquefactions, which can be understood from the stress path. So when you have cyclic mobility, you're still a little bit far away from the upper portions of the critical state line. But when you get to full liquefactions area, which means you're very close to the critical state line. So next is we talk about the before we really get into the triggering, we will talk about the subspecibility. So in fact, if I can add one more small sections for this a lecture, it will be the soil liquefaction subspecibility. So we know between sand and clay is the amount of fines. So we talk about this how much. So missing an S there. Fines there to be make sand become a silt, or how much fines there to make the silt become a clay. So again, what is fines? The soil the soil particle passing number 200 sieve. So go back to 366 when we talk about the gradation curve. So how much fines there, in order for the soils is no longer susceptible to liquefactions, and that's a difference, a research paper in the past to define that. First, come from the seed. They make use of a lot of a Chinese data, so that's why we call Chinese criteria. But be careful on that. This paper is outdated. Don't use any conclusions from this paper. It has recognized that some findings they have there is no longer valid. So even though you have the seed name over there, so it's just become a popular discussion that don't use it, even though you have the seed stem right there. So so the Chinese criteria is saying when you have a clay, the clay content is less than 15% by weight, and also the liquid limit is less than 35%, and the the natural moisture content is about greater than 0.9 times the liquid limit. So with those, if they claim if that happens, then it is susceptible to soil liquefactions. But this is outdated. Don't use it. The more recent study is by Bray, and also a Seed et al. 2003. So this Seed et al. is this is Wayman seed, and this is Harry seed. So this is the father, and this is the son. So Harry seed passed away in 1989 already. So the time after him at Berkeley, that is his son, Wayman seed. So still Berkeley work, and Bray is the student of the late students of Harry Seed. So they kind of like updated or like more corrected the criteria, and pretty much they try to do the classifications on whether it is susceptible to soil liquefactions using the plasticity chart. So this chart here tells you if like if you are within the wet area, is kind of like the boundary case. The blue area is pretty much is liquefiable. So the blue is yes. And like other than the blue and the red, that's a no. It's not susceptible to soil liquefactions. That's too the soil is too cohesive for liquefactions to be happened. But if you are at the blue, it's like a very silt like soil that yes, very likely you will be being liquefied. But when you're wet area, you may want to do like a moisture content test, whether this is like a greater or equals to 0.5 liquid limit. If yes, then like you don't have liquefactions. But if you have water content less than that, then like then well likely yes, you also have liquefactions potentials right there. So that is the susceptibility of soil liquefactions. The very first step we do, pretty much is check the adequate limits. If the soils again is outside the wet and blue area, then pretty much like you don't need to do anything about the evaluations of soil liquefactions, because the soil again is too cohesive to be liquefied. But when you have clearly a sand layers with water tables, submerged in water tables, or silt layer, or like any of the blue and red like fine materials that you have this shown in this chart, then with the underneath the water table, then your soils is susceptible to soil liquefactions, especially if this is like in California, where the area is seismically active.
Okay, so the main framework for the soil liquefaction triggering analysis involve a key concept, which is the comparisons of the loading and resistance. So very traditional, like a civil engineering framework. So that's actually like this type of triggering analysis first introduced in the 70s. So the Sid and Idris 1971. So no wonder like they embedded with this type of traditional factor safety type of civil engineering analysis when they start about this soil liquefactions engineering. So the loading is what we call the CSL. We talk for before the cyclic stress ratio, and also you compare with the CRR. So when we calculate the factor of safety, is the resistance CRR divided by CSL. So this is the triggering analysis, and we briefly talk about how to do find out the CRR, the resistance ratios. Remember from the lab that the lab approach that we talk about, we try to establish the liquefaction's capacity curve, and in that that kind of laboratory capacity curve is the liquefaction's resistance curve. It has a concept that you have certain type of loading on the y-axis, and the x-axis is certain kind of like an index. So from our lab examples that we talked about previously, so in the lab, we can count the number of loading cycle at the harmonic shear stress history, and the y-axis is kind of like the loading. If we put it is as a factor of safety equal 1, then the loading will be equals to the resistance. So we have the resistance on the y-axis, and the x-axis is kind of like a index of the type of testing you're working on. So from that, we can establish, like, based on the data point, we can establish a curve or capacity curve. So this is the liquefaction's capacity curve, which divide the key history or the evidence of like, there's liquefactions and no liquefaction. So in this case, like, the solid dock is the liquefactions that happens, and the open docks here is there's like no liquefactions being happens. So typically what is being done is, for examples, you have a bunch of SPT data. So you will have the SPT index as x-axis, and the y-axis is the for that particular, like, a site or particular event. You calculate the loading. We talk about the calculate loading. So with that, like, if you combine like a lot of data worldwide, in the old day when CNE just started, like, he took a lot of Japanese data, took a lot of like a California data, then you compile like kind of like a capacity curve, and based on SPT, then you will be able to draw out like a liquefaction capacity curve. So we will come back on this concept when we get to the specific testing methods, CPT or SPT. But that's how this being done, and how does like a liquefaction's capacity curve being drawn. So you can compare kind of like the loading. So this is some kind of like a loading, and this is some kind of resistance. So CRR is called like the resistance. You can think of like, you can be SPTM values, it can be CPT, it can be in situ shear wave velocity measurements, like the downhole and also the cross hole that we talk about. And CSR could be like, the cyclic stress ratios, which is the loading part. We can describe that with like a PGA, CSR in terms of PGA, these CAP5, the cumulative absolute velocity. So back to lecture 2, we talk about those, and also areas intensity, all different kind of like loading that or intensity measure that we describe of earthquake loading. So that could be the loading part. And at the end of the day, like, we try to compare the loading and the resistance. Then we can determine whether the loading is enough to trigger soil liquefactions. So this is from the concept paper of Sid and Idris. So he established the cyclic stress induced by earthquake here. So he through depth for a particular site, he calculate the loading, and then he established a curve for the resistance part. So this could come from the if this is site specific. So this is like the this capacity curve right here is called like global. We talk about how we will talk about a specific CPT and SPT capacity curve. But you can establish a site-specific, like a kind of like a resistance curve, and then compare with the CSR. And the resistance curve, could come from the site-specific data, and then you plot out the loading versus the resistance, and you have the locations or the depth soil layers that you will have the loading greater than resistance, and that would be the locations that you kind of like expect soil liquefactions could happen based on your design event. So now the question is how to calculate the cyclic stress ratios. So the very common method, again, is the most commonly used method is the Sid and Idris who started all this, and also we are still using it for analytical simplified procedure. Is how to convert like a PGA into cyclic stress ratios. So the whole idea is like, if you have these like ground motions, and this need to be like at the soil, right? So that's why we need to do the site response analysis to convert back walk level acceleration time history to acceleration time history at the ground surface, because that's where liquefaction happens. Liquefactions won't happen at actually liquefactions is happen at the shallow ground. If you have a vertical stress greater than 1 ATM, atmospheric pressure, is rarely happens, especially if you have like atmospheric pressures like a 3 to 5 ATM. This is starting to be like too confined or too high of vertical stress for liquefactions to be happened. So pretty much like it's a shallow ground behavior. So that's why we need to convert, or we need to like do the site response analysis to find out the response of the acceleration time history at shallow ground. So after you have that acceleration time history, you can identify the maximum point, and then you take the maximum point as the PGA. You normalize it by the G over here, and then you times 0.65 divided by the magnetic scaling factors. We will talk about this like in the next slide, and then times the total stress divided by vertical stress, and also multiplied by a depth reduction factors. We will talk about this along with the MSF in the next slide. So pretty much this is a framework for based on the acceleration time history that you design for, can convert it to become a cyclic stress ratios. Then you can do your site-specific liquefactions evaluations. So this pretty much like is kind of like a screening tool people do. Once they have their site-specific data, you want to see whether means like CPT or SPD data. You want to see have a quick check whether like your site is susceptible for liquefactions to be happens. Then you will calculate the CSR based on these ground motions. So this cyclic stress ratios, this like a line here, pretty much is plot by that, plot by like the equations here, because now these two terms, actually these three terms, are function of depth. So you can from this depth and CSR with this equations, because this is this three terms is functions of z, the depth. So you can kind of like plot out the curve there, the CSR versus depth, based on these equations, provided you have already know your PGA. So this framework, you realize that it has correction factors 0.65, y 0.65. That's based on the early work from a seed. He has some work that like also convert acceleration time history into a series of harmonic motions, such that like he can more easy to try to model the earthquake phenomenon in the lab. Because remember, back to the old days, it's not like quite possible to input a erratic acceleration time history with precisions in the lab, but simple harmonic sines forms is doable, those cyclic loading. And actually it's more practical to use like a series of harmonic motions to represent acceleration time history. So what like the seed 1975 work they had done is taking 65% of the PGA and then convert that into a series of harmonic motions. So it's about 10. So he tried to represent earthquake ground motions by a series of like 10 harmonic motions with an amplitude equals to 65% of the PGA. So that what like the laboratory modeling would do in the early days, and we are still doing it today in nowadays. So that's why, you know, this Harry said he is the father of geotechnical engineering. Pretty much he laid down the foundations for us to follow. But nowadays, like, you know, it's possible to perform like real-time acceleration time history in the lab, but yet it's only limited like increments able to do it and more for research. In practice, we still use like harmonic motions to model earthquake ground motions. So that's the equations to convert accelerating time history into a CSR. And one more comments about this method, like, you know, this method, the St. Regis method is a very good start, but for sure you also have some shortcoming. One of the major shortcoming is pretty much you are trying to representing earthquake ground motions with only one data point. So this you only consider the peak magnitude, and you ignore a lot of aspect of earthquake ground motions. You know, those temporal difference, and also the frequency difference, right? So you only use one point. You fail to describe how long the durations of earthquake may be, and also, like, you know, how the frequency content it is. You know, you could be like a soft soil response that you have many like relatively like a long period of pulses, versus like you could be a steep soil response that you have a lot of like small pulses they pack to each other. So part of it, you know, to adjust for the loading durations, it will be handled by the correction factors of the magnitude scaling factors. We'll talk about it next.
Okay, so let's further talk about this triggering models, or triggering liquefaction triggering evaluations framework, which is given this equations there. So if you look at these equations, pretty much like, you know, we try to characterize earthquake loading or earthquake ground motions by one point, which is the PGA, the peak ground accelerations. And then, like, you know, around this this intensity measure, we try to correct with different like you know, design scenario that you may have. So so you see, you come with a bunch of like a different like parameters. So we talk about the original framework from SEED. It also has the total stress divided by the vertical effective stress. So you kind of like, you know, take care of the overburdens or stress issue, because again, liquefaction also depends on the stress level you're at. And the 0.65 there is try to correct for the peak ground accelerations, because it would be too conservative if you just take the maximum loading amplitudes from our ground motions. So that's a couple correction factors to come up. First, talk about the MSF. So it stands for the magnitude, scaling factors. So the philosophy or the reason behind this is they would think the longer loading period come from larger earthquake magnitudes. So again, like, you know, if you have a high amplitude earthquake, if you have like a magnitude of 8 earthquake versus a magnitude of like a 5 earthquakes, there will be, you could expect there will be different like loading durations. So this MSF is trying to bring in the time dimensions of our earthquake events. You know, we know that like PGA is just one point, but like when you see the ground motions, you know, you can last from maybe from 15 seconds to up to like a 120 seconds. And using one point cannot capture the duration, so that the time effect over there. But the SMS try to correlate with the durations with the magnitudes. So it's very like rough estimations, but somehow, like, you know, you try to bring in the factors. So using this MSF like factors, and this graph here shows you how MSF factors change with the earthquake magnitudes, and they use magnitude 7.5 as a reference. Because at 7.5, so 7.5 is here, the MSF factors is equals to 1. So which means like what they try to do here is when you have an earthquake event that is greater than 7.5, then you get a magnitude scaling factor less than 1, and the reciprocal of it will increase the loading, the CSR, cycle stress ratios. But if you have earthquake magnitude less than 7.5, they will try to penalize your earthquake loading. So 7.5 is the reference point. And that's a bunch of different research done in the past. So that's why you see different like a different data doc over there. So the Idris one and Idris Arango. So more or less they are a little bit different, but like the philosophy behind. So you know why the difference? Very likely because they have a different database to look at, and with time you could imagine we have more and more earthquake records, especially the significant ones, such that like does MSF relationships or those equations there will be keep updating. So you know some of the correlations over there is really outdated already, especially like the 1988 or the 1983, the Japanese one. You know, I don't think any people will be using those correlations now, because one thing, like you know, some of them was quite dangerous. Is even this like embassy, like a 1988 method, you go forever high and go forever low. And this may not be true, especially for you when you have very small earthquake and a very large earthquake. So the later developments, they try to cap it with more reasonable boundary as at either like a very small earthquake or very large earthquake. So what I want you to get out from this is you understand, you know, what MSF, the magnitude scaling factor, do, and also you know keep that in mind. Those correlations or those factors will be updated from time to time, especially like you know when we get like a more and more significant data from recent earthquakes. And the other factors is the depth reductions factors. So the purpose of having this R sub D over there is to correct for the liquefactions triggering with the depth, because the deeper you go, the less likely liquefactions will be happens. So liquefactions is a phenomenon that happens at you know the shallow ground with a depth. If you get a really great depth, I don't think like you know liquefactions will happen, because the confining stress is so high that you know if you truly understand like a critical state soil mechanics, the dilative behavior of soil depends on both density and also the vertical stress, the confining stress. So when you have a very high confining stress, no matter what density you are at, very likely you will have a dilative response versus like a contractive response of the same behavior. So when you have dilative response, you're generating a negative excess pore pressure, which will increase your soil strength rather than decrease. So you may have cyclic mobility, but you know your loading and also your loading durations may not be strong and long enough to move past the cyclic mobility to the full type of soil liquefactions. So those are the two factors. And again, like this R sub D, like the MSF scaling factors, from time to time, those correlations will be updated. Because again, we will have more data to kick in, and those informations or those correlations will be changed. So this is like a very fast evolving engineering business, unlike the traditional geotechs that everything on the statics and whatever we find out in the 60s, the world didn't change much. We're still living on Earth, and so the framework and the analytical approach is still valid. But for earthquake engineering, every decade thing will we'll have new generations of models just come up. So you need to pretty much keep learning if you want to stay in this business. So this slide gives you an idea on how we establish the SPD based soil liquefaction triggering curve. So this is the soil liquefaction triggering curve right there. So pretty much like we use this for design, and this is the very first one from 1979, come out from SEET. So how he come up with this? Pretty much like the X and Y axis. So the X axis you can think of as kind of like the loading. So he calculates the cyclic stress ratios, very similar to what we have on these equations, but back to the old days, he have a even more simplified framework. So pretty much it's just like a convert maybe an earthquake record to a shear stress time history, using Liquefaction's like a site response analysis, and then divided that by the vertical stress. So he even not bother with the magnitude scaling factors and also the depth reductions factors, but that was the old days. But the concept here is from each K history. So each data point there is a K history. So this could be like the San Francisco earthquake. This could be the Japanese Kyoto earthquakes. This could be the Taiwan Chichi earthquakes. So I'm making that up, but this could be the 1999, or that's even before 1999. So 1999 has a very famous earthquake at Turkey, the Kocaeli earthquake. But anyways, each data point represent like earthquake records, and then he back calculate the loading, and then he find this on the site. He find the SPT data. So this represent the resistance. So the soil resistance represented by SPD blow count. And then he has the binary classifications, where the dark one is the where liquefactions to be happens, and the open one is there's no liquefactions happen. So remember we watched the YouTube clip together, the evidence of liquefaction. See whether you see the sand boiling on the sand ejector. Effects where they can trace the excess pore pressure being shoot out from the site. Then they will know whether liquefactions happen or not. So with those classifications, they can try to draw a reasonable boundary curve. So we call this the liquefaction's capacity curve, and then apply this kind of like a worldwide for design. So if you know your SPT, then you can have a quick estimate. You know your SPT, and then also you know your cyclic stress ratios. Then you can have a quick estimate whether you should expect this soil liquefaction is tricky or not. So that's the SPT, the old days, and I have one that quite used oftenly. So this even is not the most updated versions, but this is a very recent work that being well recognized, and I uploaded 2 papers on Canfax. So if you go to Canfax, go to 5700. So if you go to Canfax, the most updated one should be the CETN 2018 method. So that is the most updated SPT method for soil liquefaction triggerings. And for sure, I think CETN's, he pretty much you expect he built on Boulanger and Idris like a model. So so you can see the difference between like a 2012 and 1979. You have much more data points now. And the red dots means like you find the liquefaction evidence. The open dots is you don't have it. And nowadays, like deterministic analysis, you know, we try to move past that. We adopt more probabilistic approach. So they even give you 3 different probabilistic capacity curve right there. So 15% of like a likelihood for liquefactions to be happens, or 85% of liquefactions capacity curve for like, you know, for that being triggered. So it can be expressed in terms of probability, and here is their probability model. So if you want to code it, if you want to develop your own computations like a program or in MATLAB or Excel spreadsheet, you can use the code here. But if you want to do a quick analysis, deterministic approach, you know, somehow you bring in some probabilistic components right there, you know, you can just read off the curve. So all the corrections are there, the M160 clean sand, and this is truly compatible with the CSR right here that we talk about. So it has already correct for the material scaling factors, the depth factors. So you calculate everything through this triggering solid liquefaction triggering equations. So you get the y-axis, you know, the loading, and then compare with your corrected SPT resistance, the end blow counts. So that is the SPT approach. And for more informations about how to calculate the M160, this like a seed, Raymond seed, not the Harry seed. So the younger seed, the junior seed, you know, who just retired, even though like, you know, the junior seed, he retired I think a couple years ago from Berkeley. But this is his work in 2003. So he gives you at least, or he can walk you through how to correct the SPTM values from to M160 clean sand. So this gives you the details, and I encourage you to read the paper. This the Law 2003 paper. It may be a little bit outdated, but I think Professor Raymond Seed, he did a good job on explaining the overall design procedure in the Seed 2003 paper. So that's a SPT approach. Likewise, you also have a CPT approach. So if you do your site investigation program with CPT rather than SPT, so very similar concept. You have the probability state solid liquefactions triggering capacity curve right there. Again, like Boulanger and Idris UC Davis, they did a lot of good work. They both so Idris is kind of like the very first two students of the famous Harry seed at Berkeley, I think back to 60s. And then like Boulanger is the last almost the last students of Dr. Harry Seed in the late 80s and early 90s at Berkeley. So even though like I think Professor Harry Seed, he passed away in the middle of Dr. Boulanger's PhD study at Berkeley. So I end up like Dr. Boulanger's dissertation is signed off by the junior Seed. But anyways, so they both become faculty at UC Davis, and they did a lot of good work on in the topic of solid liquefactions. So that's why, like, you know, in California and also particularly in the geotech earthquake engineering's like a business is strongly influenced by the Berkeley grad. And again, the textbook that you read from Steve Kramer is also very important players or important like contributors in all this subject, as well as like Professor Jonathan Bray, and now who is still working at Berkeley. He is again one of the last students of Dr. Harry Seed. But anyways, so this is the CPT framework, and you know all this probabilistic capacity curve. And if you want to know the equations of how to come up with those curve, so this is the the CPT probabilistic capacity curve. So again, if you know your CPT values, like, you know, this chart demonstrate whether it is still like, you know, a binary classifications where like you're above the curve is liquefactions expect to be happens. Below the curve is there's no liquefactions, and between all those are kind of like the marginal case. So you need to be like for sure you need to have like a further examinations whether how likely liquefactions will happen. So if you fall between those you know, your design scenario based on loading and resistance fall between like the red and the blue curve, capacity curve right there, you know, those are the most difficult analysis or decisions that the engineers need to make. You know, whether you should treat it as, or you should do a ground improvement to avoid solid liquefactions to be happens. If your design point is out here or right there, you know, you make your choice easy. You know, for very likely, you know, nothing is 100% sure when you deal with earthquakes design, but you know, you have some sort of certainty when you are far away from those curves. But anyways, like this gives you an idea of how the CPT works, and likewise, Stokey at Texas, you know, he's the one that like one of the anti-Berkeley camp. So earthquake engineering, the geotechnical earthquake engineering at some points, like, you know, it's kind of like divided into two parties, you know, a little bit like our country now. Is the Berkeley camps versus the rest of the world. You know, could be the Texas people and also the Japanese like scholar. They have different views on how to look at this issue, and then they come up with another approach. Instead of like a last strength behavior that you use SPD or CPT, they truly believe the soil behavior or the dynamic of soil properties is dictated by small strain behavior, which means like they don't buy into those destructive geotech investigations or geotech field index like CPT or SPT, but they have put more like a faith into a small string parameters like the shear string, shear wave velocity, which is a small string behavior, small string measurements like, you know, the cross hole and the down hole we talk about in the soil dynamic properties lecture. So again, like, you know, so Dr. Stokey at Texas, so Andros is his like students. So he come up with those again, like the triggering curve. So liquefaction capacity curve, divided the data that like they find where you have liquefactions versus no liquefactions, and then depends on different scenario. You know, those are the shear wave velocity curve, which is less common in practice. I guess one of the main reasons is it's not cheap, but it's not common. You get shear wave velocity measurements running those cross-hole or down-hole tests. It's more common, you know, commonly available for those SPT and CPT investigations. Okay, so building up on the CSR stress profiles, we have two more correction factors that I want to talk about. First is the K sigma, which is the overburden correction factor. So this is correcting the overburden stress, a little bit like the depth reduction factors. So this correction factors pretty much is helps you to change, you know, to penalize the loading or to reduce loading when you're at like greater depth, which means like a higher overburden stress, or like when you're at more shallow ground, when you have a lower confining stress, it will kind of like pump up the loading, increase the loading. So that's and they use like 1 ATM or as the reference point right here. So P sub A over there stands for 1 atmospheric pressure. So which is so this is 1 ATM equals to the 2116 PSF. The other factors is what we call the static shear stress correction factors. So this one is a correction for kind of like a sloping ground. So when you have a sloping ground conditions, there's kind of like a static shear stress adding on the soil. So this is very complicated, and a lot of like research still need to be done in this subject. In the past 2 decades, I think that was the interest in the research communities on how to tackle this problems, because liquefactions in a free field, again, which means like just like kind of like an open ground, is likely not our interest, right? Because in urban settings, very likely you have pretty much your project site, you do have a building over there, and your building will be imposing a static stress to your soil elements. So you're feeling the shear stress on the elements, soil elements. So the sloping ground is one kind of like a more simple loading adding on your soil that is suspicious to soil liquefactions triggering. You'll be even more complicated when you have a building, you have structural loading sitting on a project site, where like you want to investigate the triggering of soil liquefactions. In fact, like Professor Jonathan Bray at Berkeley, focused on this subject, which is try to develop engineering procedure to find out the effect of like structural loading on liquefactions like triggering. So it's quite fascinating. You need like a very complex like a 3D modeling to look at those issues. So pretty much you need to use like a program like FLAG to help you when you get there, the effect of the structure. And like again, like if you want to learn FLAG, feel free to take the foundation of the advanced geotech design course that we offer next semester, C5670. But anyways, like the liquefactions issue here is, or this case of alpha, the correction factors is try to correct for the sloping ground. You think of that. This alpha values is equals to the shear stress divided by the vertical effective stress. So if you know your alpha values, and then like your M160 or Q CPT values there, it give you an estimate on what kind of case of alpha you should be using. And you realize actually there's quite a lot of uncertainty when you use those parameters. And I pull out those graphs from the very original work from Aegis and Boulanger, and I bet like from time to time this kind of case of alpha will make some minor change. So you need to keep an eye on how this case of alpha being changed like with time, or like a more updated like a literature out there. But again, the key concept here, the case of alpha, is for